Welcome to UGC lecture series in computer science. In this episode, we are going to discuss about the memory partitioning schemes, memory allocation and reallocation strategies. Memory partitioning is the fundamental problem faced by any operating system. The memory is always not as a single continuous stretch. It is actually available as in pieces across the total memory storage area. If it is a single linear sequence, every program consisting of several components as program, data, stack, heap, everything can be stored continuously. However, the memory is not always available as a single sequence. Out of these components, some components are dynamic, that is, the heap is something where the temporary variables and their values are getting stored during the program execution. Therefore, this tends to grow during the execution and tends to shrink during the execution. Therefore, this is of dynamic in nature. And also there is another problem, sharing of memory between the programs inside the operating system. Out of all these difficulties, the memory management has to happen within any operating system. How to divide the available memory space to accommodate all these needs? Therefore, there are two approaches by your operating system: fixed memory partitioning and variable memory partitioning. As the name indicates, fixed partitioning means there is a stable partition done within your memory. Variable partitioning tells that the partitioning inside the memory can vary during the mapping of programs to the main memory. We will now discuss the fixed partitioning in detail. In a single program system, obviously there will be fundamentally two partitions. One partition will be handled by your operating system, the kernel, which saves the OS related system programs and related processes inside that partition, and the another partition is actually given to the user. The user program and related files are stored inside this particular partition. The operating system must manage the data handling within every such partition, and the addresses or memory references from one partition, that is OS partition, should not fall inside the user partition and vice versa. Suppose if there are multi-program systems, there has to be n partitions available in a fixed partitioning mechanism. So, the partitions can be of same size or they can be of different size. If the partitions are of same size, we refer to the partitions as pages. If the partitions are of different size, we refer to the partitions as segments. Every segment is bound to have a minimum amount of memory, and maximum it can go up to the entire limit of the memory space available. The program size is always limited to the largest segment available inside the operating system. The problem which can happen here is internal fragmentation, that is, the memory space which is getting wasted after allocation of a process into the memory. This particular memory space is at the expense of the user. The user program, if it wants to grow, it can utilize the extra allocated memory and continue its operation. If it does not grow also, the extra allocated memory cannot be reclaimed until the program or until the process completes its entire execution cycle. The system should manage basically between such dynamic data structures generated out of every partition. Therefore, there are various policies which needs to be taken care of during mapping between the partitions inside the operating system. If the partitions are of same size, that is pages, which is most commonly used as an approach inside your operating system, In this particular kind of paging, the operating system must permit each such data structures or each such process component to occupy multiple partitions. The problem here is the advantage here is easy to handle, but the problem is wastage of memory, because always the memory space allocated is going to be of the same size. There is another variation in partitioning which we discussed called variable partitioning. In variable partitioning, the memory is not partitioned prior to the loading of data or a process inside the memory. Only at the demand of loading, the memory is partitioned. That is, each request is allocated a portion of memory out of the free space of memory available. Therefore, two problems can occur here: external fragmentation and generation of holes. Generation of holes, which indicates the empty memory area which are created out of the completed programs. External fragmentation occurs mainly due to the division of memory into different bits. We are going to discuss external fragmentation in detail at the later part of this lecture. However, there is one solution called coalition, where adjacent holes can be merged together so that the fragmentation can be minimized to a certain extent. There is one particular solution always available at your ease, which is called as swapping. Swapping is a process which takes temporarily a program or a job out of the mapped memory area and uses it for some other processes. Normally, there is a variation done in swapping which we call as rollout or roll-in. This variation is always happening in priority based scheduling algorithms. In such algorithms, there is a priority associated to every process. Suppose if a lower priority process is in execution, and if there is an interrupt generated due to the entry of a higher priority process, and the higher priority process now demands the memory area for its execution, now your operating system intervenes and stops the lower priority process, checks it out of the memory temporarily and loads the higher priority process inside your memory and continues the execution. Only after the completion of the higher priority process and the release of the total memory space, the interrupted lower priority process which is swapped out can be loaded back and continued the execution. There is one particular component which is importantly to be noted during this swapping, which is called as transfer time. The transfer time occupies a major part of the swap time. Total transfer time is proportional to the amount of memory swapped. If you are going to swap a 2K memory for a 4K memory, the time which is taken to swap out a 2K memory, load a 4K memory process and load back, that is swap out this 4K memory process and load back the old 2K memory process. The time taken for all these 4 steps is actually accumulated to a transfer time, and we refer to this as total transfer time. Therefore, if a larger process is getting swapped out, the total transfer time is obviously becoming larger. What if there are more processes than which could fit into a particular memory area? Obviously, swapping is going to be a solution, but which is not a permanent solution. The intelligent decision has to happen during the allocation of the process into the memory, so that with a minimum amount of swapping and not wasting too many overhead in swapping, the operating system will be able to do the memory management successfully. This is how a swapping happens inside your operating system. There is a monitor or user area, operating system area, and this is the user area. And the disk obviously houses the user programs. User 1 is the program which is stored in the disk. Now this program has to go for execution. This is loaded inside the memory area which is getting executed. Now if there is another higher priority process called user 2 which is coming for execution, the user partition loads back the lower priority process user 1 back to the backing store or secondary storage and loads back the user 2 and continues the execution. And after the full completion of user 2, it is basically loaded back to the secondary storage and next the process is to load back the suspended user 1 into its original memory area and to resume its operation. Therefore, the total time is taken to swap in and swap out both the user 1 and user 2 is actually known as transfer time. The contiguous allocation is a fundamental issue to be noted during swapping. If your particular the operating system process is loaded prior to the swapping in a suitable memory area, to certain extent the swapping of processes can be minimized. So obviously the main memory has two partitions as operating system partition and user partition. The OS partition is in low memory. Low memory we refer to the low memory as the start of the address 0 and the user processes are loaded after the loading of the operating system processes. Therefore, the relocation registers are playing a major role in protecting the user processes, not referring to the operating system processes. Base and register and limit register are the pair of registers which are involved in the process of relocation. The base register is houses the smallest physical address or the smallest memory address from which a process has to be loaded. The limit register gives the entire range of logical addresses or the entire sweep of a memory area up to the process can be loaded. That is, each logical address which is getting generated as a memory request, it can be a read request or a write request. This logical addresses has to be less than the contents mentioned in the limits register and therefore we refer to the name of the register as limit register. So this is how the address protection happens inside your relocation registers. The CPU generates an address and first the address is checked with the base register. Base register, you can remember we said the base register houses the start address of the process. Therefore, the address generated by the CPU cannot be lesser than the contents of the base register. If it is greater than or equal to the contents of the base register, only then it is a valid request. If it is a valid request, it is now passed on to check the limits register contents. If it is not a valid request, the interrupt is getting generated and a trap is generated inside your operating system to stop the entire process. The valid request goes on to check with the limits register. The request is again checked with the limits register. Now the address has to be less than the limits register, only then it can be valid. If it is still valid, the real request is given back to the memory. If it is not valid, that memory trap is getting generated and the process comes to a still. Now we will discuss the features of memory allocation, which is very important inside any operating system. This diagram tells you how fundamentally a memory is allocated inside the operating system. Operating system basically maintains the information about the allocated partitions and free partitions inside the memory. In the figure, the operating system has 3 processes under execution: process 5, process 8 and process 2. Assuming if process 8 is getting completed and is chucked out of the memory, there are only 2 processes remaining, process 5 and process 2. The gray area tells you that there is a hole which is generated out of the completion of a process 8. Now, if any other process requests its allocation, it can be given room in this memory area provided it is within the limits of this particular memory area. Assuming there is another process 9 coming inside for want of a memory area. It is given allocation, and even then there is still another segment of memory which is created as a whole. If some more process called process 10 comes for execution, it is also given room inside the available memory space, and therefore you can now visualize the larger whole is gradually getting smaller and smaller, and once this whole is becoming very small such that it cannot be allocated to any other process, the operating system stops allocating the processes inside the memory. This is how the memory allocation happens inside the operating system. There are certain issues in memory allocation. This is basically a challenge. The allocation of memory is basically a challenge in variable partitioning mechanisms. The fundamental idea is, if the partition is varying, the available memory space, that is the available whole which is created, will be also varying. If there is no prediction about how much amount of memory will be wasted after completion of the available processes, it is hard to achieve the performance of any operating system. Therefore, the criteria which is basically followed in memory allocation is speed and best utilization of the storage area. There is a concept of dynamic memory allocation which is becoming a solution for the issues which we discussed. In dynamic memory allocation, the name itself is mentioning you that the memory is allocated only at the time of request. There are 3 variations in dynamic memory allocation, which is called first fit, best fit and worst fit. Every variation has its own benefits and shortcomings. We will discuss every one of them in detail. The first fit memory allocation tells that allocate the process to the first available whole inside your memory. Best fit tells allocate the process such that the remaining amount of whole generated is going to be very small. Worst fit tells you that allocate the process such that the remaining amount of whole generated is going to be very large. Only the policies differ. However, every such mechanism will be producing a particular memory space called whole, which can either be utilized or cannot be utilized. It depends on what policy you prefer for allocation of memory. Therefore, fragmentation is always a problem which can never be eradicated, but to some extent can be managed intelligently. This is how the example of best fit and first fit goes. Assuming there are 2 memory areas 1300 and 1200 which you have in your memory, and assuming there are 3 requests arising out inside your operating system. The request 1000, in first fit approach, the policy says allocate the particular process to a memory area which is first available. The first available is 1300 and therefore the process is allocated to 1300, the remaining whole is 300. So, we have written 300 comma this 1200 is not at all allocated to any other process. Assuming there is another request 1100 coming inside, it goes and analyzes the first whole is of size 300 which cannot be allocated to 1100 because this is much lesser space. Next whole available is 1200 which can yet be allocated to this 1100. Therefore, this 1100 process is allocated to this space, so the remaining whole generated is 100. Assuming in the third step there is another process which is coming of size 250. The available holes are 2 of size 300 and 100. The first available hole itself is large enough to accommodate this process. Therefore, after accommodation the remaining hole is 50 and the second hole is 100. This is how your first fit algorithm works. The same allocation can happen in your best fit algorithm. Assuming 1300 and 1200 memory space, the request 1000 is going to be allocated to a best fit, that is smallest hole possible. Therefore, it is now allocated to this 1200 and the remaining hole is 200. The 1100 request can then be allocated to only this hole, because this hole is very less to very small space is there to accommodate the 1100 request. Therefore, it is allocated to this particular hole. The remaining space is 200. Assuming the third request comes 250, total memory area is of size 400K, which is still very large enough to accommodate this request, but it is of two different partitions. Therefore, every partition, though it has 200, the request is of size 250, and therefore the process cannot be allocated to the memory even though you have the available memory. Therefore, for this particular scenario, the first fit policy proves better. Best fit policy has a struck inside your operating system. The same variation, we have another problem with the request 1100, 1050 and 250 for the same available process. Here, the best fit algorithm, as we discussed earlier, efficiently handles the situation. However, the first fit policy, after allocation of 1100 to 1300 memory space, 200 hole is generated. After allocation of 1050 to this memory space, and 150 hole is generated. However, the third request can never be entertained. Therefore, both the best fit and first fit approaches have their own advantages and disadvantages. Therefore, the efficient policy always would be the worst fit approach, because the hole generated will also be large enough to accommodate a forthcoming process inside your operating system. These holes we call as the result of fragmentation. Fragmentation can happen as an internal or external. Internal fragmentation, which we mention as the fragment which is generated inside the total allocation. Suppose the memory area from this area to this area is totally allocated for the process A. There is still room for growth for process A, and if suppose the process A does not grow during its entire execution, this particular memory area is going to be wasted. This memory area is called fragment or internal fragment. This can never be reclaimed and utilized. Only intelligent allocation of the total available space will minimize the internal fragmentation. Now comes the external fragmentation, which is resulting as a part of the completion of a process. So, here is the OS, here is the process 3, process 8 and process 2 mapped. Here is a 50K hole, here is a 100K hole which is free. However, an 125K process will never be accommodated inside this hole and this hole. Therefore, there needs to be, these both are called external fragments. These must have been created after a 50K process going out of this place and a 100K process going out of this place. Now, in total there is 150K, but it is of two different parts. Therefore, it cannot be allocated to this particular process. Therefore, there needs to be a mechanism which accumulates or which gathers all such bits of memory into a single memory, and we call this mechanism as compaction. In compaction, the same example we discuss here. In compaction, the process 3 and process 8 is moved either upwards or downwards. Both possibilities can happen. In this diagram, the process 3 and process 8 are moved upwards, so that the two different bits of memory holes available are compacted or joined together to form a single large hole, such that the process 9 can be accommodated. In a variation B, both the processes are moved downwards, so that here the process can be accommodated. The compaction can be recommended as a solution only if a relocation can happen as a dynamic kind of relocation. If process 3 and process 8 cooperates with you with the dynamic relocation policy only, you can do such kind of compaction at time of execution. Otherwise, this will not be recommended as a solution for external fragmentation. Another solution is coalescence. In coalescence, it is much similar to the compaction, but the problem is we don't always bring variable blocks inside your memory to join together. Instead, we only take care of two adjacent blocks which are made as a wholes, so that they can be joined together to form a single memory segment. That is, when two free blocks are adjacent to each other only, they can be merged as a single block. So, in this example you can see, if there is a B, A, C processes going on inside your memory and process A is completed and released, B and C are getting generated as two different bits, coalescence cannot happen. Here assuming BAC is there, C is already an available free area and the shaded area is indicates the process. Assuming A is also released, so two adjacent blocks are now released, therefore coalition can happen and it can be assumed as a single memory space. In this variation, the area B is already free, A and C have the two different processes going on. If A is released, these both can be merged together to form a memory area. Remember, there is difference in the naming convention. So, the naming convention goes like this way: the available whole is merged with the previously available whole, so that it is named by C dash. The previously available whole is C, so the new name given is C dash. Here the available whole is B. Right now the process A is released and therefore the new name given is B dash. Here B and C are always already available, and if the A is released, the name goes this way, it is named as B dash, and the entire three regions can be combined together to form coalition. However, this is an example of hybrid coalition. This is not a simple coalition. This involves two fundamental steps. First, the area B and A is combined together to form one whole, and the combined whole along with C is again combined together to form another large whole. So, this is a solution of external fragmentation. So, therefore, there are various benefits and pitfalls of compaction and coalitions. Compaction is generally time consuming, but applicable for relocatable processes. We have to be careful in doing compaction, and it takes time also. In coalition, it takes very less time and no hardware support and easier in general. There are, however, other solutions to fragmentation called paging and segmentation, which we will discuss in the forthcoming lectures. Let us summarize what we have seen so far. We have discussed about the swapping, variations in swapping, the allocation of memory, and the varieties in memory allocation called best fit, worst fit and first fit, and the comparisons between the memory allocation schemes, external fragmentation, internal fragmentation, and the solutions of the fragmentation schemes. Let us now discuss a few questions. Question 1. What happens during a swap operation? Question 2. Mention the use of base and limits registers. Question 3. Can fragmentation be totally avoided? Question 4. Where do the operating system store the contents of base limit register? With this, we have come to the end of this episode. In the forthcoming episode, we will discuss paging as a solution of external fragmentation in detail. Thank you.